Let us now study characteristics and applications of different types of DC motors. Now we have to study three important motor characteristics. First characteristic is between armature torque TA and armature current IA, that is TAIA characteristic. This characteristic is also known as electrical characteristic. Then the second characteristic is between motor speed N and armature current IA, that is NIA characteristic. And the third important characteristic is between speed N and torque TA, that is NTA characteristic. It is also known as mechanical characteristic of motor. Now before discussing these three characteristics, you have to remember two important relations. First is armature torque TA is proportional to phi into Ia. Means torque developed in armature TA is proportional to the product of flux per pole phi and armature current Ia. And a second relation is N is proportional to EB upon phi. Means speed N is directly proportional to the back EMF EB. And you know that EB is equal to V minus IARA. And N is inversely proportional to flux. So as flux increases, speed decreases. Now we will see these three characteristics for different types of DC motors, that is for DC shunt, DC series and DC compound motors. Let us now see characteristics of shunt motors. So first characteristic is TAIA characteristic, that is characteristic between armature torque TA and armature current IA. So here torque TA is on y-axis and armature current IA is on x-axis. Now this is a shunt motor, means field winding is connected in parallel to armature, and as field is connected across armature or across the supply, field current IF is almost constant. If IF is constant, flux phi is also constant. So in case of DC shunt motors, flux phi is practically constant. Actually, at heavy loads, because of armature reaction, phi decreases slightly. However, practically we can assume that flux phi is almost constant. And if phi is constant, you know the relation for torque, TA is proportional to phi into Ia. But in this case, phi is constant. And if phi is constant, TA is proportional to Ia. So in case of DC shunt motors, armature torque TA is proportional to armature current Ia. So if you plot the characteristic between TA and IA, then it will be a straight line passing through origin. So in DC shunt motors, TAIA characteristic is a straight line passing through origin because TA is proportional to IA. The shaft torque TSH is slightly less than armature torque TA. So between TA and TSH there is a difference due to iron loss and frictional loss, and therefore the torque available at shaft TSH is less than TA. So here TSH, it is shown by a dotted line, and TSH is less than armature torque TA. So here you have to remember that in case of DC shunt motors, starting torque TA is only proportional to Ia, and therefore starting torque is low, and therefore shunt motor should not be started on heavy load. Let us now see the second characteristic of shunt motors. It is NIA characteristic, that is characteristic between speed N and armature current IA. So here speed N is on y-axis and armature current IA is on x-axis. Now N is proportional to EB upon phi. In shunt motors, IF is almost constant from no load to full load, and if IF is constant, phi is also practically constant. So if phi is assumed constant, N is proportional to EB. So in shunt motors, if phi is assumed constant, N is proportional to EB. Now EB is also practically constant because you know the expression for EB. EB is equal to V minus IA into RA. RA is resistance of armature. So as IA increases, IaRa will increase and EB will decrease. But as RA is very small, the change in EB is also very small, and therefore EB is also practically constant. So if EB is constant and N is proportional to EB, then ideally the speed of shunt motor must be constant from no load to full load. Actually, in case of DC shunt motor, when we increase the load, we have seen that EB decreases. At the same time, flux phi also decreases due to increased armature reaction. Now, if EB decreases, N decreases, whereas if phi decreases, N increases. However, EB decreases slightly more as compared to phi. So when the motor is loaded, EB slightly decreases and N is proportional to EB, and therefore the speed curve of DC shunt motor is slightly drooping as shown by this dotted line. So when load on the motor is increased, speed of DC shunt motor slightly decreases. For all practical purposes, we can consider DC shunt motor as a constant speed motor. Means its speed remains almost constant from no load to full load. Let us now see the third characteristic, that is characteristic between speed N and torque TA. So here speed N is on y-axis and torque TA is on x-axis. Now this characteristic can be derived from first two characteristics. So here, first characteristic is between torque and armature current. So here, when armature current increases, torque increases, and the increase in torque is linear. And the second characteristic is between speed and armature current. So when armature current increases, speed of the motor N slightly decreases, and therefore with increase in torque there is slight decrease in N. So the characteristic between speed and torque, it can be plotted. With increase in torque, there is decrease in speed. So this is the speed torque characteristic of DC shunt motor. Let us now see characteristics of series motors. So first characteristic is between armature torque TA and armature current IA. Now in case of motors, TA is proportional to phi into Ia. Now here the field winding and armature both are connected in series, and therefore the field current is same as armature current Ia, and therefore flux produced by this field winding, it is phi, which is proportional to Ia. But this is true up to the point of magnetic saturation. So before saturation, phi is proportional to Ia, and therefore TA is proportional to IA into IA, that is IA square, and therefore before magnetic saturation torque TA is proportional to IA square. So here TA is proportional to IA square at light loads, and therefore the curve is a parabola as shown here. So when the load current is small, that means before magnetic saturation, TA is proportional to Ia square, and therefore the curve is like a parabola. But after magnetic saturation, when the field poles get saturated, you know that flux phi remains almost constant after saturation. So if phi is constant, TA is only proportional to Ia, and if TA is proportional to Ia, means the characteristic is a straight line. So after saturation, the characteristic curve is a straight line, and before that it is a parabola. So in this case, the again shaft torque TSH, it is slightly less than armature torque TA. Now in case of series motor, you can see that the starting torque is high because TA is proportional to Ia square, and therefore series motors are used where a huge starting torque is required for accelerating heavy loads quickly. So whenever high starting torque is required, DC series motor is more suitable. Let us now see second characteristic of series motor, that is NIA characteristic between speed and armature current. Now you know that N is proportional to EB upon phi. Now in case of series motor, EB is equal to V minus IA into RA plus RSE. Now RA plus RSE is very small, and therefore the change in EB is also very small, and therefore change in EB in case of this motor, it can be neglected. So if EB is assumed constant, N is inversely proportional to phi. Now here field winding and armature are connected in series. Now when load on the motor is increased, Ia will increase. Same current Ia is flowing through the field winding. So flux phi will also increase. So here as load increases, flux phi also increases. And with increase in flux phi, there is reduction in speed N, and therefore speed varies inversely as armature current in case of DC series motor, and therefore it is shown by this inverse characteristic. So here as the load or armature current is increased, speed of motor N, it decreases. Now here you have to note one important thing. Now suppose armature current Ia is equal to 0. So if it is 0, current through field winding is also equal to 0, and therefore flux phi is equal to 0. So if phi is 0, speed will become infinite. Means if the load on the motor is small, then armature current Ia is also very small. And for small armature currents, speed of motor can become dangerously high, and therefore DC series motor, it should never be started without some mechanical load on it. Means first of all we have to put load and then only we have to start DC motor, because if it is started at no load, then current drawn by the motor will be very low, and if the current is small, speed can be dangerously high. And therefore, DC series motor should never be started without some mechanical load on it. Now, series motor, you can see here, it is not a constant speed motor. It is a variable speed motor. Its speed varies with change in load current. Let us now see the third characteristic of series motor, that is NTA characteristic. So this NTA characteristic, it can be found with the help of first two characteristics, that is TAIA and NIA characteristic. So here you can see that when the speed is high, then the torque is low, and when the torque is high, the speed is low. And with this information, we can conclude that with increase in torque, speed of the motor N decreases. So here, as torque increases, speed decreases. So the characteristic will be inverse. So this is the shape of characteristic. So in case of DC series motors, as torque increases, speed of the motor N, it decreases. Third type of motor is DC compound motor. Let us now see characteristics of DC compound motors. So compound motor is a combination of series and shunt motor. So these motors have both windings, series and shunt field windings. Now there are two types of compound motors. Cumulatively compounded motors means series magnetic field and shunt magnetic field both are in the same direction, whereas differentially compounded motor means its series field opposes the shunt field. So here, in case of cumulatively compounded motor, as we increase the load, there is addition of two fluxes, shunt field flux and series field flux. Whereas in case of differentially compounded flux, series field flux is subtracted from the shunt field flux. So flux decreases as load increases in case of compounded motor. Now the shape of these curves can be adjusted by adjusting the degree of compounding, that is by adjusting number of turns of series and shunt field windings. Now, if you see the cumulatively compounded motor, then in this case, as flux increases with increase in load, torque also increases. So, in case of cumulatively compounded motors, starting torque of the motor is high because the series flux and shunt flux gets added at light load. After saturation, series field flux remains constant. Now here in case of cumulative compound motor, you can see that as load is increased, there is increase in flux because series flux gets added to the shunt flux. So as flux increases, speed decreases, and therefore with increase in armature current, speed of cumulatively compounded motor decreases. And the third characteristic can be drawn by first two characteristics. Now in differentially compounded motor, flux decreases with increase in load and therefore torque also decreases. Now here with decrease in flux, speed of motor increases, and therefore with increase in load, speed of differentially compounded motor will increase. So here we can say that cumulatively compounded motors are suitable for heavy machine tools with pulsating load. Pulsating load means the load is variable. Now it is suitable for heavy machines because its starting torque is high, and it is suitable for pulsating load because it can be operated even if the load is zero. We have seen that series motor cannot be operated with zero load because its speed will become dangerously high in case of light load conditions. But in compound motor, both the windings are present, series as well as shunt. And that's why with cumulatively compounded motor, we can obtain high starting torque. At the same time, the motor can be operated at heavy load, and therefore it is suitable for heavy machine tools with pulsating loads. Whereas differentially compounded motor, with increase in load, flux decreases. So as we increase the load, there is reduction in flux, and therefore there is increase in speed, and therefore the motor may become unstable if the motor is not properly designed, because in this case, as we increase the load, speed of motor goes on increasing instead of decreasing. Let us now see applications of DC motors. So first type of motor is DC shunt motor. So the characteristics of DC shunt motors. The speed of DC shunt motor is almost constant from no load to full load. Then its speed is adjustable. It can be controlled by flux control or by armature voltage control, and its starting torque is medium, and therefore DC shunt motors can be used for constant speed applications and where medium starting torque is sufficient. So it is used for applications like lathes, centrifugal and reciprocating pumps, machine tools, blowers, fans, etc. Then the second motor is DC series motor. Now series motor, the speed is variable, it is not constant. Then in case of series motor, the starting torque is high. Then in this case also the speed is adjustable by field current control or by armature voltage control. But one important thing is series motor cannot be operated without mechanical load. If it is operated without load, then its speed becomes dangerously high, and therefore DC series motors are suitable for applications in which high starting torque is required and variable speed is permissible. So these motors are used for electric traction, that is electric locomotives or trains. Then these are used for hoist and cranes, conveyors, trolley cars, etc. Then third is cumulative compound motor. So cumulative compound motor, in this case also the speed is variable, they, but it is not as variable as DC series motor. Then starting torque is high. In this case also the speed is adjustable, and here the motor can be operated without mechanical load. So in this case, even if the load is reduced to zero, then also the speed will remain within limits because of the shunt field winding. In compound motors, both windings are there, shunt as well as series, and therefore because of shunt winding, it can be operated without mechanical load also, and therefore these motors are suitable for intermittent high torque loads. Means sometimes the torque is very high and sometimes the load is almost equal to zero. In that case we cannot use series motor, but we have to use cumulative compound motor. So these motors are used for shears and punches, for heavy planers, in case of rolling mills, etc., where the load is pulsating. Then differentially compounded motors, these are rarely used because in this case the operation is not stable. Thank you.